My name is Taketo Sano. Today I'd like to talk about this interaction between mathematics and computers. So this is the third time I'll be giving a talk in this coffee. And as I'll be a member of this newly established mathematical application research team, today I'd like to focus more on this computational aspect of my research. So first, if you pick any random mathematics book, then I think you'll see something like these, statement like this. So this is the definition of a group. You say a group is a set G together with a binary operation satisfying the following. And then you'll see something like this. A ring is a set R together with two binary operations. And if you're a mathematician, then you're basically used to these kind of statements. So these are just the start point of this argument. But if you're not a mathematician, then maybe you might not like these kind of formulation. So you might feel that these are very meaningless and abstract, kind of vague expressions. So, but if you are a programmer, or at least if you know how to write code, then there's a way to understand these statements in a more kind of programming kind of way. So I'd like to give some kind of introduction to those kind of way of seeing these statements. So there are quite nice correspondence between concepts in mathematics and programming. So first, in mathematics, we have sets. So this Z is the set of integers, Q is the set of rational numbers, R is the set of real numbers, and so on. And mathematics is basically based on these sets. On the other hand, programming, there are types. So we have type of integers, and we have type of strings and arrays, and so on. So these are kind of similar. And on the math side, we have elements. So we say that the number 2 or 3 are elements of this set of integers Z. On the programming side, we have instances. So we say that 2 is an instance of the type int. So it's very similar. And we also have functions in mathematics. So this GCD is a function that takes a pair of two integers and returns an integer. Similarly, on the programming side, we have this GCD function that takes a pair of two integers and returns integers. And furthermore, in mathematics, we have many structures, and those structures form hierarchies. For example, we have sets, and we have monoids that kind of extend this an additional structure on the set. And we also have groups that's more additional structure on this monoid. And on the programming side, we have this abstract types and inheritances. So we have this kind of group is an extension of a monoid, and also monoid is an extension of a type set. So, and I'd like to focus on this final line. So as we remember, we saw this kind of mathematical definition of a group. And then we can understand this as a group is an abstract type that is required to have this binary operation called multiplication, and this identity element E, and this inverse operation. And we can say that this type group extends this type monoid, which has this multiplication and unit, but not necessarily the inverse operation. So this group, the group type extends this monoid type. And of course, monoids are set, so it's like set monoids extending this type set. We also have this additive version of these operations. So we have addition plus and this additive identity element 0. And we also have this additive group. Sometimes we call it an Abelian group. So we have this plus and 0 and also this negation operation. So plus can be negated in this additive group. Now, a ring is a combination of monoid and additive groups. So we have addition and negation and multiplication and 0 and 1. But not necessary, there is not necessary the multiplicative inverse in this structure. So this definition of a ring can be kind of reformulated like this. And then above this ring, we have this field where we can invert all non-zero elements. So we can think of these mathematical structures as this kind of hierarchy. So I created a demo program to kind of demonstrate this kind of hierarchy of structures. Yeah. So this is a programming language called Swift, and it's pretty nice that we can write in a pretty mathematics-oriented way. So first we have this protocol is something like an interface or type class if you're a Haskell, or a trace if you're a Russian. Oh, so it's basically an abstract type. It's a declaration of abstract type. So first we consider set, and then we say a monoid is a set endowed with these two additional structures. So we have this multiplication. It takes two elements or two instances of this type, and then returns this the instance of this type. And we also have this identity element. And then what these two operations must satisfy is that this multiplication must be associative, meaning that A times B times C is equal to A times B times C. And also this element being an identity means that it's basically doing nothing if you just multiply with identity. It's like an element 1 in the integer. So these are the things that we require to have for multiplication and identity. And then a group is a monoid that is also equipped with this multiplicative inverse called int. So any instance of this group has an inverse, and if you multiply A with its inverse, then we return this identity. So this is what we kind of see in mathematics textbooks, and we can express this like this in a program like this. Now we have an additive group. So this has this addition plus, and we have this additive identity 0, and we also have this additive inverse, which we denote by this negative sign. And now, if we require to have this this type to have these three operations, then we can define this subtraction by A minus B is defined to be A plus the additive inverse of B. So then if a type has these three operations, then we don't need to implement this minus operation because we can define it like this. So I'll show you I'll show you in a moment where this is. So now again, we require this additive group to have this commutativity. So A plus B is equal to B plus A. And then we have this associativity. We have this 0. This is additive identity. And we also have that this negation operation is the additive inverse of A. So we have A plus minus A is 0, and minus A plus A is 0. Now, I'd like you to recall the diagram that this ring is an additive group and a monoid combined that also satisfies this distribution law. So A times B plus C is equal to A times B plus A times C, and also on the right side. And then we say that a field is a ring, which is equipped with this multiple inverse in it. So you might think that this is similar to what we require for group, but a field is not a group because in a field we only require that in a group all elements must be invertible, but in a field all non-zero elements are required to have inverse. So these are different concepts. So field is not a group. Anyway, so if we have this field, then we can define this division by A divided by B is equal to A times the inverse of B. So this now we have this abstract type called field. And I'll get to this Euclidean ring later, but we can see that these are abstract types that we define can be implemented by concrete types. So in usual programming language, we have this built-in type of int, which represents an integer. And then this already implements these plus and minus and those operations. So we only need to implement the missing function. So here we declare that this type built-in type int is a monoid and is an additive group and it's a ring and also a Euclidean ring. So we only need to add these two functions. So it's 0 and ID. So in this case, 0 is the number 0, and this identity is the number 1. So now we can test here that, so we let A equals 312 and B is 68. And this percent, this is an reminder operation. So if we divide A by B, we get this reminder property. So we can see that the result is 40 here. So I'll get back to this Euclidean ring. So this Euclidean ring it's called Euclidean domain in mathematics, but it's a ring that has this reminder operation in addition. And if we have this reminder operation, then we can implement the GCD function. This is the greatest common divisor, and it's also called the Euclid algorithm, which basically we can keep on taking the reminders for two of these numbers, and then we get to the finally we get to this greatest common divisor at the end. Mm-hmm. So if a type that conforms to this Euclidean ring implements this reminder operation, then we automatically get this GCD function. So we didn't implement this GCD for this integer, but because we have this GCD here as a default implementation, we automatically get this GCD function for integers. And now we see that this GCD of these two numbers is 4. So we didn't implement this, but we get this for free. So I would show you another example of this Euclidean ring where we can get this GCD for free. So now we have this rational numbers. This is known to be a field. So it's a set and additive group, monoid ring, and a field. So this is basically this implementation, rational numbers. So these are basically rewriting what we learned in elementary school. So we have this addition, and we have this negation, we have this multiplication, we have this additive multiplicative inverse, and then we get this implementation of a rational number. So this rational 2, 3 corresponds to 2 over 3, and this rational 5, 7 corresponds to 5 over 7. And then we get these operations. But here, for this A minus B and A divided by D, we didn't implement the function because we just implemented the additive inverse. This is the negation operation, and also this multiplicative inverse operation. And by implementing these two functions, we automatically get this A minus B and A divided by D. So this is just rewriting A plus negative B as A minus B. A divided by B is A times inverse of B. So we get these functions for free. Now, this polynomial is known to be a Euclidean ring when this base ring. Sorry. So this is a polynomial type. So polynomial is like a sequence of. So we take this R as a generic parameter, and we consider this polynomial over R. So this is written as R of x in mathematics. So this can be expressed as a sequence of these coefficients. So it's a implementation of this polynomial type. So we just do the implementation like this. So we define this addition and this negation, multiplication, but we don't have this division because if we divide a polynomial by a polynomial, we usually don't get a polynomial. But if this base ring R is a field, then this type R of x becomes a Euclidean ring, meaning that we can do the reminder operation for polynomials. I think you learned it in maybe high school mathematics. So we have this percent operation for this Euclidean ring, this polynomial f and g. And the way we define it is basically we kind of subtract the highest term until the remainder becomes, the degree of the remainder becomes strictly lower than this dividing g. And here we're doing this implementation here, but we need this base ring R to be a field in order to divide these lead coefficients. So this R being a field this is required so that we can actually do this operation here. But at least if R isn't field, then we can do this operation and we can define this reminder operation like this. Now, so we consider this base ring R as its rational numbers, And then we define these elements A and B. So here this -3, 0, -2, 0, 1. This corresponds to the coefficient from the lowest degree. So this corresponds to x to the power 4, -2 to the power of 2, and -3 as a constant term. Similarly, this -2, 1, -2, 1 is corresponding to this x to the power of 3 minus like this. And then we can define this addition, and then this subtraction and this multiplication. And the point here is that we define this reminder operation. So because these rational numbers, these are fields, this is a field. So we get this type, polynomial type over this Q is a Euclidean ring. So now we can define this reminder operation like this. And then because we had this, we automatically get this GCD function for free. So we didn't implement this GCD function for polynomials, but because we know that this polynomial over this rational numbers is a Euclidean ring, and we define this operation here, we get this GCD function for free. So the greatest common divisor of this two polynomials A and B is x squared plus 1. So we automatically get this for free. Okay. So this is exactly what we saw now. So basically, if we have this kind of hierarchy of structures, if we get some kind of functions or maybe some propositions using only these abstract structures, then the concrete types or these concrete objects, mathematical objects, inherit all those properties for free. So that's the beauty of abstraction and inheritance. So if you are not so much, if you don't like those kind of mathematical formulations, to me, implementing those mathematical concepts in programming is like building Legos to me. So when I was a kid, I very much liked playing with Legos, and also my kids love playing Legos. So it's like kind of building mathematical concepts as actual code and trying to make those kind of structures make sense and use those structures to actually do nice computations, so that we don't need to repeat those concrete implementations every time, and we get this nice abstract properties for free for actual types. So this is the end of the talk. Thank you for listening.
Thank you very much, Sano-san, for very interesting talk between the computational science and mathematics. Okay, any questions?
I was looking at your code and it seemed like, so because it's all inherited, so if we look at the drawing you made, it's all inherited all the way up.
Yeah.
But when you were making declaration, you kept restating even the more lower one, not just the highest one. Like when you made, I think, ring, or I can't remember exactly, but I think like you were including monode and additive group. You couldn't just say ring.
Yeah.
Like way up there, when you were making the declaration, you had several of them linked one after the other. Maybe further up, I think. Maybe. I don't know where. Yeah. You have like instead of just naming normally inheritance, you just name the highest one, and it inherits everything below. But in this case, you explicitly have to name all of the ones below plus the latest one.
I think just for simplicity, so I think we can just write it.
Okay. Okay, that wasn't the confusion. Okay, thank you.
That's just if this is not allowed, even this is not allowed, it's just a restriction of this programming language. So,
but if you're allowed to put these extra terms, is it ever possible that you could accidentally create a conflict?
Yeah.
Because it seems to be super defined, like over defined.
That's the restriction in programming. So in mathematics, we might override. So there might be some confliction where things might mean different things in different contexts. For example, if mathematicians might write a identity matrix, that's one, but that one is different from the one that's
right.
Matrix. But people can understand those differences, but computers might not be that flexible. So that's the kind of difference. When you...
I see. Okay.
But yeah.
Yeah, I have a stupid question. In this case, you have like multiplications and additions, so you can implement the concept of group into computer. But for example, let's say more abstract things like abstract like geometry or geometrical structure. Like, oh, is it always possible to somehow implement?
I think that's a very different kind of difficult question to answer, because obviously we cannot express all real numbers as codes, because only programming can handle up to finitely many things, and there are uncountably many real numbers. So you cannot. It's not true that all mathematical concepts can be implemented like this, but we can formalize mathematical concepts in these. For example, this programming language called Lean allows us to write mathematical proof computer program. So in that sense, we can formalize math in programming, but that's not the same as saying that we can express this, for example, this pi as this kind of concrete in this program. So that's quite vague thing, and we have to, when we want to try to implement things in computers, we have to think about the restriction that we can handle. So basically, when I write computer programs in my research, I don't use real numbers, but I use these rational numbers instead, because we cannot handle real numbers in this precise way. So for example, the square root of 2 times square root of 2 is not equal to 2 in programming, because the precision of those floating point numbers is not perfect. So in order to do exact computations, we have to choose the right mathematical structure. Not so things don't go wrong in programming. So that's a very subtle point.
You have to know math very well, and also how computer works very well.
Yeah.
You
can't do things for operation.
Okay, we have a question from Kodama-san. Kodama-san, go ahead.
Yes. So I personally do not understand what's the good point of this language or this computation. I mean, so what can we do from this as a mathematician?
Oh, so yes, that's a very good question. So in my research, I do computations for Kobana homology. That's a homology group that's assigned to knots, and we can think of those homology groups over any commutative ring. For example, we can take integers, or we can take rational numbers, or we can take a polynomial ring over some field. And we never want to repeat writing those computations for each of those specific types. So if we implement those computations in a generic way, so that we can switch these base rings when we want, then we can write those computations in a unique way, so that we don't need to repeat writing those for specific types. So that's the idea that I was trying to present for this GCD function.
Compared with another language, the good point is it is easy to define type, very difficult type.
So
right?
there are many programming languages, so you can choose whichever you want. So I choose this one for demo because it's quite easy to read. But in my actual research, I'm using this programming language called Rust, which has this kind of nice inheritance property, and there's more kind of direct way of handling. So you can choose whichever you want, but there are features that specific programming languages do feature, and some don't. So you have to choose which fits your needs. And yeah, so someone might like C++, someone might like Java, someone might like Python. So it's up to you. So you can choose whichever you want. So
Yeah,
you-
yes,
you-
of course, I can use, but what I still do not understand what's the good point of what you introduced. So it's about defi what you told was about defining new type. And
So it's about understanding these mathematical way of expressing mathematical ideas in a more kind of programming um, perspective. So if you look at these kind of definitions, it
yeah,
might
definition. Yeah, there is a if there is a definition, we can write down a type. That's and yeah, even in Python, for example. And what's the difference using Python and using this kind of language?
yeah, there are many differences. There are many specific differences. So some language might support objective-oriented programming, and some might support these functional programming. So it's if
Yeah,
you're
it should be different,
yeah,
but I didn't understand what's the difference.
yeah, because that's something I didn't present in my talk. So that's some kind of
I see.
programming. Yeah, yeah. So
Yeah, okay,
I need to connect the mathematical idea and programming. So
okay, I see. Yeah, okay, that's enough. Thank you very much.
I think in terms of the benefit, maybe you can mention the fact that you can use it to verify long proofs so that it reduces the amount of effort required to review like math papers.
you mean about lean?
No, yeah, Leans and I think formalization in general benefits mathematics research in the sense that it can reduce the amount of labor required to verify results if we can formalize it in the language that we can trust. So that's probably what you could respond to his question in terms of what's the benefit of doing this in the first place. And I think
Oh, I see. What's the benefit of formalizing math in? Yes. So yes, but that's a bit different from what I wanted to present. But there's a thing called computer assisted proofs, and we can formalize mathematical proposition and their proof as programming languages. And if you write down those in a nice way, I mean, writing a correct program means that that proof is correct. So we can rigorously write proofs in a way that we write programs. So if that's completely written down, then we can very strongly trust that that proof is correct. And then there are many libraries, so you can use those. But yeah, then so writing proof and doing computation is kind of a different thing, but there are of course intersections.
So can I understand like you have a mathematical idea and right now you give just some representation. It's like a decimal or binary computer system.
Yeah.
But now all the mathematical idea can be represented in a binary or a decimal system. Okay. And you also mentioned you also can do a proof for some system or.
So the way I don't think we can do differential calculus in this kind of way because we cannot express real numbers. But you can formalize those properties that real numbers possess, and using those you can write formal proofs for those things. But doing actual computation is something a bit different. So I don't want to say that all mathematics can be implemented in a way that is computable, but there are things that we can do about it.
Can you talk about more detail about your math theory? How do you connect to your computation program?
In my research,
In your research, you say you use Nast theory, something.
oh, Rust, not
No, he says when you're doing not.
Nast theory.
oh, not theory. Ah, I see.
How to connect to your
So the theory that I'm working on is defined combinatorially. So if you have this knot diagram that can be expressed as a four-valent graph. So this, if you have a crossing, that can be understood as a vertex, and those edges coming out from that crossing can be understood as edges. So knot diagrams can be represented as a four-valent graph, and then you take that as an input, and then you do those kind of combinatorial definition inside the computer. And then if you get those, if you can represent those objects in that breaks down to linear algebra, then you can do anything you want, because linear algebra is kind of yeah. so if you want to implement mathematical theory as a computer program, you have to think about how you can express those ideas and computations as computer programs. And then if you succeed to do that, then you can just plug in concrete examples and see the computational results. Thank you.
Where,
It's related to Namba-san's question. In your mind, what would be apparently most difficult mathematical object or concept to computer?
If things break down to combinatorics, then that's quite easy to handle. So if we can do things in finite, at least in principle, in those finite sequence of computations, then that's very likely that we can. It involves some kind of transcendental operations, or maybe, for example, real numbers are transcendental. So those are very, there's a huge gap between.
I see something requiring infinite.
Yes. Uncountably infinite things may be very difficult, or at least you have to think about how you turn those things into essentially finite. I think that's the huge difference between computer programs and what we handle.
Well, do example from sets like ring, field, and monoid. What if you have function? So you give some property, let's say Cauchy quantity or linear function. And can you also define a function by giving a property this function?
A function. So
yeah. So let's say you have to solve a functional equation. And give this function equation as a rule.
Yeah.
And then can you do this?
If there's an algorithm, then I think you can implement it. But for example, if you think about this, mean something there. For example, if you want to write a program that finds the actual point where this slope is equal to this, then I think that's only possible in an approximate way. So
how is the approximation?
Yeah. So in mathematics, there is this existence theorem where they only state the existence but not the actual.
Find it.
Yeah. So. Yeah, that's what's up. Yeah.
That's been always my frustration with math. They just want to prove that there exists a solution. I just want an approximation. So there's a different interest.
Right.
So that's what he means. They can prove that there is a solution. Good for you. No, we'll find it.
Yeah. So that's I think that that's one very So having those constructive proof is also nice in mathematics. So if that's constructive and also combinatorial, then there's a very good chance to have that in computers. But if it's only just stating the existence, then we have to find a way to actually find those things that are close to that, or some kind of exact way to find that exact solution. So.
Well, I have a very naive question. Namely, people say that AI can do almost everything in the future. Then how you define the creativity which cannot be done by AI? Can you define?
I think that's impossible to answer because we still don't know the limitation of AI. So we don't, in order to answer that, we have to know the limitation of our brain and also the limitation of AI. But those are both, I think, still under research.
We also have to define creativity.
Yeah.
Missing, most importantly.
So if computer can only do this kind of brute force searching, then there's a chance that human can find a nicer way to approach. But modern AI can also do this kind of vague
approximation.
Yeah, so it's kind of getting very. It's not easy to answer. It's very.
We can say it has intuition.
Yeah. But it's still at this point, for example, if I ask some mathematical question to ChatGPT, then that returns some kind of nonsense answers. So
Yeah, a lot of time.
I'm sure at this point there are many advantages for our students. But, yeah, but in the future, I don't know how much those. Maybe in some day computers might exceed human mathematics. So we have to find a way to cooperate with AI and also find a way to how we can work together with AI instead of competing with AI. So, yeah.
Okay, thank you very much. So
one more question.
Question about the limitation of this approach. So I think you point out the common thing between mathematics and programming language. But I guess programming language was designed so that you can do like mathematics.
Yeah.
Yeah. So do you have a comment on like how much complex structure mathematician can handle, like using like beyond the force design by computational linguistics?
Can you repeat the question again?
Do you have a comment on how much complex structure can you approach beyond the engineer's first design? I think those like groups or rings are already designed in computational like programming language.
Yes, for example, we have this programming language called Lean, and I think in principle that language can formalize every mathematical concept. So in that sense, it's already well built enough. So, yeah. Yes. So there are very complicated differences. What those differences are built upon, but basically we can think that because we say that mathematics handles infinite, but these mathematical books are written in finite many pages. So at least and also we can understand proofs that some kind of finite sequence of these modifying these propositions and those symbols. So in that sense, all mathematics should be able to be
based on
yeah.
You could design.
Yeah. But doing actual computation is a different thing. So even if you can formulate mathematics, it doesn't mean that you can compute everything. So yeah.
Okay, so at this point, maybe we can thank Sano-san again for his very interesting talk, and thank you very much for everybody for the good debate. Okay, I'll just stop facilitating and leave the common room for the further discussion. Thank you.